Good morning, this is Cody Hendricks, and today we're going to be looking at doing graph traversals. So we're using this data structure of a graph. We're looking at how we can actually go over those structures using the two main traversal methods of depth first or breadth first. So we're going to take a look at the logic first, and then we're going to go from the logic and actually look at the code for our implementation we're using here in C++. So we're going to take a look at the traversal type specifically. Our first types we want to look at is when we're dealing with a data structure that is not linear in its framework, aka a graph or a tree. We have to actually look at how we're going to decide to look at that data. And with a tree, we actually have those three traversals we looked at, the idea of the in-order, pre-order, and post-order traversal, where it has some predefined structures. But when we're looking at a graph, it's actually a different way of doing that. We don't have that same concept of first and last, like we had automatically by default when we're looking at a binary search tree, where it's, there's a clear beginning and a clear end, based on the idea that there's some order to the data. When we're doing the graph, however, instead of having that idea of that order data like that, we have the idea of our data. We have to find a way of actually going through and finding the information and looking at what it is. And so we're going to use a couple different ways of traversing that data to look at that. And so we're going to use the traversals to actually address that. Now, a couple of things we have to make sure we address with the idea of our traversal. One is the idea that we can't guarantee that every node is going to be reached if we have a directed graph. Because a directed graph can have nodes that only point away from themselves. If we don't use that node as a starting point, we will never actually hit that node. And so we'll take a look at that in a later lecture. But on the idea right there, you can't guarantee that all nodes will be hit versus when we have, say, for the idea of an array or array list, where we can go and hit every single node in order, boom, 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 boom. It's automatically and easy to go. So just FYI for that. Our different approaches to actually approach that data, we have the idea of either going deep, going as far down as we can, or we can go spread out across the data for the graph itself. And that's how we're going to be looking at this with the idea of either depth first or breadth first for addressing these. So let's go ahead and first look at the depth first traversal. As for a depth first traversal, one of the first things we have to do is we have to declare an array of Boolean values. These declare whether or not it's been marked or not. We're going to call it marked vertices in class. And so that marked vertices array just says, oh, have I seen this vertex or not? Yes or no. It's a quick way of identifying whether or not we've been there, because we don't want to waste time going to vertices we've already hit. So we just have a Boolean array, we can deal with that. And then we're going to recursively process and mark each node or vertex in our structure. And then we'll pass its neighbors and go and process using that recursive approach to go through and process and mark each of those vertices as well. So the approach on that is the idea that we have the recursive helper method. We go through and pass it the information from that array and access it from there. So to take a look at the code for it, we have first the idea of our depth first code, our main method, the external one, or the public method they'll be using on that. As you can see right here in our public method, we have two parameters. We pass it a tree itself and the vertex, because we can pass it a not a tree. We could pass it a subgraph or part of the graph, and we have passed it the vertex we're going to be dealing with on that. We first create our array called marked vertices. We pass it that maximum, because again, we're only going to be dealing with a max set on this. We're not doing a big data structure. We're looking at our graph structure for this project. And then we call assert, making sure that our vertex we're doing is actually less than the size. We don't want to try and do vertex of 5 billion when there's only 40 things in the list, or 40 things in the graph, excuse me. We're then going to use a special method. Notice how I have the std scope resolution fill underscore n call right there. And that scope resolution fill n, what that does is it says, okay, we're going to fill this data structure that's in the first parameter, in this case marked vertices, for the number of options, in this case graph.size, and we're going to pass that the false value for every one of those spots of size worth inside the vertices array. So what I'm going to do is I'm going to take that vertices array and I'm going to fill it with a default value. In this case, I'm taking the vertices array and filling it with false values. Because in C++, we don't have that guaranteed association of value on that, especially if we're going to say, for example, put these objects in here. In this case, we're only using primitive Boolean variable, but that makes it easier to put all those values right there for immediately, because we want to assume that we haven't visited all of these spots first. Then once we mark that array all as false, we then go through and we do our depth first traversal. And so this is, again, we're using that same method name because it's the idea of using a recursive method. Again, we're going to be doing a void-based recursion. And with a void-based recursion, remember, we don't have to have the idea of returning a value that we're going to build off of. Rather, we're doing a process over and over. And that process will stop when it's done. So we don't really have a base case. We just have the recursive case. The base case means we're done. We're out of there. But on that recursive call we have right here in depth first traversal, notice that we have, in this case, we have 3 parameters we're passing it. Instead of the depth first traversal with our external or public call, this depth first traversal takes the same idea of the graph and the vertex we've already used, but then it also adds as a parameter the marked vertices array. So we have the idea that we're going to pass a reference to that, we're going to pass that array in there so we can actually go through and use that marked vertices array to actually go through and access that information. Also with the idea that std underscore, or scope resolution fill n, we could just make a loop to go through that array and actually fill that array with that data type of false in that case. But using a one-liner right here of fill_n does that work for us rather than having to have a loop and have a couple lines of code attached to it. We have an already pre-built method inside C++ that has that attached to it. So we might as well use that extra method for it. So our next thing we want to look at is our recursive helper method. This is where the major work happens inside our depth first search. And so again, notice that we have on our header right here, I'm using a bool pointer marked vertices. Again, remember an array itself is actually a pointer. And so because I had it as array as my previous call, I can simply refer to it here in my header for my method as a pointer because an array is really just a pointer to that type that has memory attached to it. So that's the same reason we have that right there. Then I'm going to take a look at the actual idea of our call right here. We first have inside that, we have an idea we're making a set. And remember again, a set is that type of a set is a data structure that has no duplicates. It is a so in this case I could have it's of type int, so I could have 1, 3, 5, 7, but I couldn't add another 1 or another 5 or 7 because I already had those values already in that structure. And then what is assigned in that is our neighbors method. Our neighbors method grabs all the neighbors of that current vertex and attaches it from there and passes it into the connections variable. So we now have the connections set that has that information in it. The thing we're adding new to this is when you make sure you grab in your notes, we have the idea that we're adding an iterator to this. And so an iterator is a built-in type that allows us to process a data structure. In this case right here, I have a type set int iterator. So I have an iterator that can go through a set of ints, and that set int iterator can go through and actually grab the information and process that entire data structure one at a time. This is what is at the heart of a Java for each loop, where it's the idea that it can go through and get everything in that list. And so we're going to be see how to do that here inside our code in just a second. But an iterator is that tool that allows us to actually go through and process an entire data structure without having to know where things are inside that data structure. It's very helpful. Once we have that iterator built, we then want to go ahead and grab our individual spots. Again, the idea of a recursive depth first traversal, we want to mark our locations. We want to say, oh, I've now visited this spot. So in that case right here, I set mark vertices at vertex. I set that value to be true because I've now seen that vertex. My next step that we're going to do is we then print out our vertex spot because, oh, here's where I am. I'm going to process that vertex by printing it out. I could also have this process, instead of having to print out, I could add this to, say, for example, an array list, or dump it into an array so I could have that, so it could store it in a value. But the idea of processing, simply right here, I'm just going to dump it out to an output format so I can have it right there. The next thing we have right there is our iterator for loop. We're going to use our iterator to go through and actually look at every single element of our graph. And remember, the idea of this, we're using that iterator as that built-in data structure tool that we have that can actually process that and hit every single spot. So in our initialization section of our for loop, we do set iterator is equal to connections.begin. And so connections as a set right here, the begin method on that set allows us to move it to the very beginning of the data structure. So that means we're going to be the first one in that set. And then we're going to use the set iterator, and then we're going to go through as long as it's not equal to end. So end is not the end of the data structure itself, it's actually after the last value. So as long as we're not after the last value, we'll keep on repeating this loop over and over again. And then, amazingly, just like when we're using a regular for loop, we do set iterator ++, which adds to the iterator and processes it to the next one. And so an iterator right here is basically just a special kind of pointer that allows us to actually go through and process a built-in data structure. And so this iterator is going to save us lots of time. It's a very helpful tool to use inside that. Now, because our iterator is also a pointer, we have to make sure we look at this and refer to it properly as a pointer inside our code, which we'll see here in this next line. So the next thing we check is make sure we haven't already looked at the spot. So we check to make sure that we're not already marked this in our vertices. So we check to see if mark vertices is not true. And we pass it the dereference marker, aka the asterisk, of set iterator. Because we want to go the value at this iterator already in there. In this case, is that vertex in that array? If it is, then we don't do anything. However, if it's not in there, then I'm going to go ahead and I'm going to do depth first traversal again on that, passing now the dereference indicator, in this case set iterator, and the marked vertices array, and the current graph again, so I can go through and process that again. Notice right here, I do not have a base case. If I no longer match that case, if this doesn't happen, I just simply dump out and go back to my previous location. And so then I'll mark that associated location true and repeat that call as necessary until it's done. So this is the depth first. I go as deep as I can, repeatedly going deeper and deeper until I can't go deeper further, and then I pop back out of my recursive tree and grab those values. So that's where we're going with the idea of the recursive structure to actually get that out. So that's for the recursive helper. So I'm breadth first, so now I want to go wide. So a breadth first traversal means I'm going to go as wide as I can inside my structure first. And this traversal is a little bit different. We're not going to use a recursive search. On this, we're going to just use a loop for this. And we're going to talk about how that's set up. So again, with this one, we're going to process and mark a vertex. And then we're going to add the neighbors of that vertex to the queue. Now, who remembers using a queue data structure earlier? We talked about queues. We're going to start off with, we process the first vertex in our graph. The next step is we grab all the neighbors of that graph, and we're going to add it to a queue. So we're going to grab the neighbors, add that to a queue, and then as long as that queue is there, because a graph, again, is a first in, first out data structure, we'll process everything that's at that front part of it. We pop that out of the graph, or excuse me, we take that out of the queue, process that node, grab all of its neighbors, if it has any, add those into the queue, and repeat that process over and over again until that queue is empty. And so we keep on adding unmarked neighbors to the queue until it's over. And so it's a different structure on that. And so let's go ahead and let's take a look at the code for it. So the code for this is a little bit different. So we have in a breadth first traversal, as you can see right here, it's a much larger method, but it doesn't use a helper method for it. And so in that method right here, we start off with, again, passing the graph and the vertex, just like we did on the depth first traversal public method. This one also fits inside our public section. And if I take a look at that right here, I have a Boolean array, just like we did earlier, of maximum size. And then I create, again, a connections set, where we're going to have a set of type int. We also make an iterator for that, so we're also, again, going to iterate over that set of int type. But then we also add to this a queue of type int. And so to add that queue of type int, we're going to have to make sure we do pound include. And we want to do pound include, and then inside angle brackets queue to make sure we get access to that. So just make sure you add that inside your .cpp file as well. We also, again, still need to assert to make sure we're actually in the right size. Again, for some weird reason, we don't want to do too much when we're doing it. Then, we use that same std underscore fill in, and then we're going to fill that data structure with the appropriate value. Where we get different right here, we're going to process that vertex, but instead of calling a recursive helper method, notice right here we have a loop. And we push that vertex onto the queue. As long as that queue is not empty, we're then going to grab all of its neighbors. We'll pop off that one that's in the queue, so we're done with it now because we've actually processed it already. We then go through and use our iterator again, and we're going to grab everything starting at the beginning of that for all of its connections. And we're going to, as long as that has something that's not been processed, we add it to the queue. We process it, in this case, again, by cout statement. Again, like I said earlier, you could do that processing by dumping it to an array list, save it to file, or some other approach. But right now, we're just using the idea of doing a cout because it makes it easy. We then push onto that queue again, that new reference to the iterator, that value of it. Again, we're dereferencing what's at that iterator spot, so we grab that value of the node that's stored inside the graph, and we then process that again. And so that process loops over and over and over again until the queue is empty. Both of these data structure traversals get through as much as possible of the graph itself. However, the graph itself is traversed in a different way. When we, just like we have the difference between the in-order traversal and the pre-order traversal, as well as the post-order traversal on a tree, the breadth first versus the depth first traversals on a graph give you a different set of information. So if you go over depth first, it's going to grab a different order to the path than you would inside a depth first traversal. So the idea here is that we have different ways of grabbing that information, and because we have different ways of grabbing that information, we're going to use them in different actual processes. And again, when we're using a graph, we're using this to model something in the real world. A graph is often used to show some problem, like say, for example, how we're going to make a traveling cells problem. How do I get from one part of a city to another? Or like it shows in the textbook, how do I have an arrangement of flights so I can cross the country effectively? Say, for example, I want to actually do a sales presentation in a bunch of different places. How do I arrange my flights to make the best possible direction with that? And that is done with using a graph-based algorithm. So that's where we're going with this, and they did different traversals. So we have, again, right here, we have our traversal of breadth first and depth first. Our depth first has the helper method that goes with it. The depth first traversal just starts off with that quick little helper line right here. We then go to our recursive helper, which does all the majority work on that. Again, process that information, where we go through and recursively call that until we have nothing else to call, because it's using a void-based recursion, so it doesn't do anything separate from that. The other option, again, is to go to our breadth first traversal, where it adds items to another data structure, a queue. And again, like I said, when we're using the graph data structure, it really takes advantage of other data structures, like a 2D array, like a list, like a queue or set, so it can build the actual answers for it, because a graph data structure is really good at using other data structures to do the work. So that's where we come into play with that. And so that's where we have the idea of doing traversals using a graph.